Welcome to Understand the Math. This video is part of a series of videos on linear algebra and its applications and covers section 1.1, an introduction to linear transformations. I'll teach you what a linear transformation is, go over example problems to help you understand the terminology of linear transformations, and teach you how to describe a linear transformation geometrically. Be sure to check out the link below for free guided notes that you can highlight and fill in as you watch this video. Let's begin by understanding what a linear transformation is. In mathematics, a transformation refers to an operation that moves or changes a shape, figure, or function in a specific way while preserving certain properties. It's a way to map an object to a new position in the same or a different space. Transformations are used widely in geometry, algebra, and linear algebra. A transformation in algebra that you're probably already familiar with is this transformation, which shifts our function f of x to the right by c units. Let's now talk about what transformations in linear algebra look like. A transformation in linear algebra is a function that maps vectors from one vector space to another, or possibly the same vector space, using matrix multiplication. We write this transformation as t of x is equal to a times x, where a is a matrix and x is a vector. This transformation is called a matrix transformation and maps x to t of x, which is also equal to ax, and we also sometimes call that vector b. It's called a matrix transformation because it can be written as a times x. Let's look at an example so that you can see what a transformation in linear algebra looks like graphically. We have a matrix A multiplying a vector x, and this is equal to minus 1 plus 4, which is 3, and then minus 3 plus 6, which is also 3. This vector is equal to t of x, or b. Our vector x here in our picture transforms into our vector t of x. When we work with transformations, we'll use a lot of terminology which you might not yet be familiar with. I think the easiest way to understand this terminology is to first review some terminology that you used when you were studying algebra. Let's look at the function f of x is equal to x squared. The domain of this function is all the possible input values. That's going to be values of x between minus infinity and infinity. The range of our function is all actual output values. The range is going to be values starting at 0 and going to infinity. The codomain, which you might not be familiar with but is really important in linear algebra, is a set of all possible output values for any function in the xy plane. And that's going to be between minus infinity and infinity. Let's now look at these same three terms in the context of linear algebra. Our transformation maps x to t of x, or ax, or b. Let's remind ourselves that A is an m by n matrix, x is an n by 1 column vector, and then t of x, or ax, or b is equal to an m by 1 column vector. This means that x is an element of Rn, and then t of x and ax and b are elements of Rm. The domain of a linear transformation is the set of all possible input vectors. Referring to our transformation above, that's the set of vectors Rn. The codomain is the set of all possible output vectors, or the vector space that the transformation maps to. In our transformation above, that's equal to Rm. Now let's look at the range or image. That's the set of all actual output vectors. Notice that now we're talking about actual instead of possible. This is also a subset of the codomain. We usually refer to the range or image as our vector B. Lastly, the preimage is the set of all actual vectors in the domain of a transformation that map to a specific vector in the codomain, such as vector B. In our transformation above, this is just our vector x. Let's now walk through 3 example problems so that we can understand how the terminology that we just learned is used in practice. In our first example, we're asked to find the domain and codomain of the transformation t of x is equal to a times x. Because we want to find the domain and codomain of the transformation a times x, let's write down ax and then look at the size of a and of x. We're given that A is a 4x4 matrix, so that means that x has to be a 4x1 column vector. This then means that t of x, or b, also has to be a 4x1 column vector. The reason for that is these two numbers need to be the same, and these two numbers need to be the same. Our vector x is in R4, and it maps to our vector t of x, or b, that is also in R4. So we say that the domain is R4, and the codomain is also R4. Whenever we have a square matrix, the domain and codomain will always be the same size. Let's now look at part B. We're given that A is a 5x4 matrix. We'll write down A times X and then plug in our sizes. A is going to be 5x4, which means that X is 4x1, and then that in turn means that A times X, or B, is equal to 5x1. Our vector X is in R4, and it maps to our transformation t of x, or ax, and that's in R5. Our domain then is R4, and our codomain is R5. Let's now look at part C. We need to notice in part C that the matrix and the vector that we're given is just A times X. Let's now write down their sizes. A is 3x3. Our vector X is 3x1. And that gives us a transformation that has the size 3x1. So our vector X is in R3, and it maps to t of x, which is also in R3. Notice that the matrix is a square matrix, which is why the size stays the same. Our domain is R3, and then our codomain is also R3. Let's now look at our second example. We're given a transformation that maps a vector in R2 to a vector in R6, and we're asked to find the size of matrix A. Our transformation R2 to R6 means that X is an element of R2, and that t of x, or ax, is an element of R6. When we look at the size of A times X, we see that X is a 2x1 column vector, and it's going to map to a 6x1 column vector, which means that this number has to match this number, which is going to be 2, and that this number has to match this number, so our first number has to be a 6. This tells us that A is a 6x2 matrix. Our third example has 3 parts, and it's based on our transformation T of x is equal to AX, where A is this matrix. Before we begin, let's notice that A is a 3 by 2 matrix, and X is an element of R2. In part A, we're asked to find the image of vector 2 minus 1 under the transformation T. If we want to find the image of vector 2 minus 1, that means that our vector X has to be set equal to that vector 2 minus 1. The image that we want to find is our vector B, and it's equal to A times X. Matrix A times vector X is equal to our matrix A, 1, 3 minus 1, minus 3 minus 5, 7, times our vector X, which is 2 minus 1. Doing our matrix vector multiplication, we get 2 plus 3, which is 5, 6 plus 5, which is 11, and then minus 2 minus 7, which is minus 9. This vector that we just found is the image of vector 2 minus 1. Let's now look at part B. In part B, we're given vector B and then asked to find X, whose image under T is B. This means that we need to find X from the equation AX is equal to B. To find X, we're going to construct the augmented matrix A augmented with B, and we're going to put it in reduced echelon form. Let's go ahead and do that. We have our matrix A, 1, 3, minus 1, minus 3, minus 5, 7, and we'll augment it with our vector B, 5, 11, minus 9. I'm going to skip these steps, and I'll write down our reduced echelon form. Before we write down the answer, let's remind ourselves of the sizes that we're working with. If we write down A times X, we know that A is a 3 by 2 matrix, which means X is a 2 by 1 matrix, and that's the solution that we're looking for. If we circle our pivots, our reduced echelon form matrix tells us that our vector X is going to be 2 minus 1. Let's highlight that answer. Let's now look at part C. For part C, we're given that B is a vector 3, 1, 0, and we're asked to find out if B is in the range of T. I think the hard part about this one is figuring out what to do. B will be in the range of T if AX is equal to B has a solution. This means we need to take A, augment it with B, and put it in echelon form and see if a solution exists. Let's do that. We have our same matrix A, 1, 3, minus 1, minus 3, minus 5, 7, and we're going to augment it with our vector B, 3, 1, 0. I'm going to skip the steps, but here's what it looks like in echelon form. We have 1, 0, 0, minus 3, 4, 0, and it's augmented with 3, minus 8, and 11. Notice that in our echelon form, our matrix has a row of zeros equal to a non-zero number. We know that this means that there is no solution. This tells us that B is not in the range of T. Let's now talk about how we can know if a transformation is a linear transformation. A transformation T is a linear transformation if it preserves the operations of vector addition and scalar multiplication. Vector addition and scalar multiplication can be written algebraically like this. Notice in number 2, if C is equal to 0, we get T of 0 is equal to 0. These properties tell us that in a linear transformation, all grid lines remain parallel and the origin remains fixed. Let's now look at an example of how we can use these properties. We're given that we have a transformation from R2 to R2, and it's a linear transformation, and it maps a vector U into a vector 1, 2, and it maps a vector V into the vector 3, minus 1. We're asked to find the image under T of 2U plus 3V. That's where we're going to start. We're going to take the transformation of 2U plus 3V, and we're going to use the properties above. We're going to pull out the constants and take the transformation of U and V separately. This gives us 2 times T of U plus 3 times T of V. This is equal to 2 times T of U. T of U is the vector that U mapped into, which is this vector. That's 1, 2, plus 3 times T of V. T of V is the vector that V mapped into, and that's this vector, 3 minus 1. Multiplying everything through, we're going to get 11 and 1. This vector is the image under our transformation of 2U plus 3V. Let's look at one more fact about linear transformations. If a transformation cannot be written as a matrix transformation, it is not a linear transformation. Let's use this example to better understand that fact. Let's begin by writing this transformation in vector notation. Notice the entries in each vector are separated by a comma. Our transformation in vector notation looks like this. We have T of x1, x2 is equal to x1 plus 1, that's the first component, and then the second component is 2x2. We want to see if we can write this as a matrix A times our vector x, which would be a matrix A times x1, x2. Let's focus on this term right there. Because of that term, we're not going to be able to write it as A times x1, x2. Instead, we can only write it as 1, 0, 0, 2 times x1, x2. That gives us the x1 in the first component and the 2x2 in the second component. And then we have to tack on a constant vector, 1, 0, to account for the 1. We can think of this as a matrix A times a vector x plus a constant vector c. And this is not equal to just A times x. This tells us that our transformation is not a linear transformation. Any matrix transformation that involves a translation is not a linear transformation. Let's also notice that we could have put in the 0 vector and computed T of 0. If we do that, x1 and x2 are both 0, and we would just get back a 1 and a 0. And this is not equal to the 0 vector. Geometrically, this means that the origin does not remain fixed in place. Now that we know a lot about linear transformations, let's talk about how we would go about describing a linear transformation geometrically. Linear transformations modify vectors in a way that preserves the underlying structure of the vector space, such as straight lines, the origin, and linearity. Just as we said before, this means that all grid lines remain parallel and the origin remains fixed. Linear transformations can perform various operations like rotation, scaling, reflection, shearing, and projection. We're going to learn a lot more about all of these in the next section. For now, we're just going to look at 3 examples of these transformations. We're going to learn what we need to do to describe what each linear transformation does to an arbitrary vector, xy. Our starting point with all of these examples is to compute t of x. This is equal to a times x. So we'll plug in our a, 0, 1, 1, 0, and we'll plug in our arbitrary vector xy. This is equal to y and x. To see what this looks like on our graph, let's plug in a vector for x and y. We can choose that vector to be 2, 1. And then when we multiply it by our matrix A, we get vector 1, 2. Let's graph these vectors. Our vector x is 2, 1. And then our transformation is vector 1, 2. Looking at our graph, we can see that our transformation reflects our green vector over the line y is equal to x and becomes our purple vector. Let's write down that our transformation reflects the vector about the line y is equal to x. We'll study more reflections in the next section. Let's now look at our second example. Just like we did for the first example, let's begin by computing t of x. That's going to be 2, 0, 0, 2 times our arbitrary x vector xy. Doing the matrix vector multiplication, we get a 2x in the first component and a 2y in the second component. Since we have a 2 common to both components, we can pull the 2 out and write this as 2 times vector xy. This transformation scales every vector by a factor of 2. Let's now look at our third example. T of x is going to be equal to a, 0, 0, 0, 1 times our arbitrary vector xy. And what we get is a 0 in the first component and a y in the second component. This means that this transformation projects every vector onto the y-axis. Be sure to check out the next video in this series where we'll study more transformations like this and learn how to find the standard matrix of a linear transformation.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.